This is FET206. Which of the following, which will be shown on the next slide, is a logic circuit from which the same output is obtained as the logic circuit shown in the figure below? Here, this symbol represents the logical product, the AND. Here, this symbol represents the logical sum, or the OR. And this symbol represents negation, or the NOT function. And here we have our list of circuits, one of which will perform the same operation as the circuit on the previous slide. So let's first start by drawing out our circuit. So we had two inputs, A and B, and the circuit that we had was A and B, and the B was then inverted, and this was placed into an OR gate. So we had these two terms ORed together. So let's convert this into Boolean algebra. We have x is equal to A and B, and this is then ORed with, so we can use the plus, the sum operator, not B. And so this is our Boolean algebra expression. So what we can do is we can invert the output twice, just so we can use De Morgan's theorem on this set of Boolean algebra. And this doesn't change any of the logic at all. So then what we can do is we can firstly apply De Morgan's theorem to this term here. So let's just highlight that in red. So we're going to apply De Morgan's theorem to this summing sign. So what we will have is this is then equal to A and B knotted, ANDed with B, which was inverted twice. So we can see that this double inversion here is going to be got rid of. So this is just equal to B. And then we can move on to the next line. So here we're now going to apply De Morgan's theorem to this sign here. And so we're going to equate this to not A or not B, ANDed with B, all inverted. So what we can do at this stage is we can actually expand out this set of algebra. So we can say this is now equal to not A and B, or not B and B. So not B and B is always going to equal to 0. So if we say something is equal to 0, and then we OR it with something, we have just this term giving our output. So we can basically ignore this whole side of the expression. So this expression simply becomes not A and B all inverted, because this not B and B is equal to 0. So then what we can do is we can use De Morgan's theorem again one more time on this operator here this time, and this will equate to A or not B. And so our X output is actually equal to A or not B. So let's analyze the circuits we had and see if this matches with any of those. So this just shows how we went through the algebra on the previous slide. So first of all, the logical circuit was given by this expression. We then double invert the expression so we can apply De Morgan's theorem, first of all to this operator, giving us this output, secondly to this operator, giving us this output, and then finally we can expand this term into this term. We used the simplification that not B and B was equal to 0, and any expression ORed with 0 was equal to just the expression itself. So therefore we have this output, and by applying De Morgan's theorem one more time to this operator here, this was our output. So let's look at the logic circuits that we have in the previous slide. So in this case, our X is going to be equal to A ORed with not B. In this case, our X is going to equal A and not B, all inverted. In this case, our X is going to equal to A and B, all inverted. And in this case, we have A and B ORed with A. So this is what x equals in each of these cases. And what we can see, though, is that very clearly this is equal to when we applied De Morgan's theorem on the previous slide. So as we can see here, our x is equal to A or not B, and by applying our De Morgan's theorem on the more complex circuit, we get the same answer. And so here, the same results can be obtained from A. So A is the correct answer. So our correct answer was A, and here we've learnt to apply De Morgan's theorem to a slightly more complex circuit and compare that to other equivalent circuits to see if they match with our De Morgan's theorem simplification.